Hello and welcome to the start of week 5's lecture. So we're going to start off by figuring out how to determine a rate law. So if you remember, a rate law is an equation that says, the rate of the reaction is equal to some constant times by the concentration of the reactants raised to some power that you've got to determine experimentally. So how do we find this rate law? Because we can use this law to predict how fast a reaction will take place. There's a lot of different ways you can try and figure out a rate law, but in this class we're going to focus on the method of initial rates. And basically what we're going to do is we're going to measure the initial rate of the reaction, and we're going to know the initial concentrations of the reactants. And the reason we focus on the initial rate is right at the start of the reaction, the reactants have a fixed concentration. And so if we look at our rate law expression here, we'll know the concentration of A, we'll know the concentration of B. Right at the start of the reaction, we can measure the rate. And so that just makes it a lot easier to handle when everything here and here and here is essentially a constant. And then all we have to do is we have to find out the value of K and the value of X and the value of Y. And that allows us to determine a rate law. So just to complete our notes here, so if we know the initial concentrations of reactants, then we can just measure the initial rate. Now, what we're going to have to do is we're going to have to do multiple experiments here. So each experiment's going to give us one bit of information. And so we've only got one bit of information. We can only solve one thing. So if we've got a rate law up here and we don't know the value of K, and we don't know the value of X, and we don't know the value of Y, that's three things that we don't know. And we're only measuring one thing. We're measuring the rate. And I guess we know the concentration of A and we know the concentration of B. So if we're only measuring one thing, we can't solve for three different unknowns. So we've got to do multiple experiments. And so if there's three things we need to know at least three different experiments to figure it out. All right, so let's go to another slide and let's have a look at a reaction and let's try and solve for a rate law. So let's say we've got a chemical equation up here. So it's NO2 plus CO. These are all gases, by the way, but I'm not going to write the state symbols in. It goes to NO plus CO2. And we can go ahead and we can write a rate law. We can go ahead and we can say the rate is equal to a rate constant times the concentration of NO2 raised to some power. We'll call that X times by the concentration of CO raised to some power. We'll call it Y. So this is our common form of a rate law. And we don't know three things, right? So we don't know K, the rate constant. We don't know X, the order with respect to NO2. And we don't know Y, the order with respect to carbon monoxide. And you might say, well, don't we actually? I mean, isn't it just 1 and 1? And the answer is not necessarily. So it may be through sheer coincidence, just like a stopped clock can be right twice a day. But we have to do experiments to solve for those orders there. And here's the way we're going to do it. So we're going to start off with I guess 4 different experiments. So I'm going to write a little table here. And let's do it in white. And so I'm going to put experiment number up here. So experiment 1, we're going to start with a concentration of NO2. I'm going to put a little 0 down here, and that 0 is telling me that that is at the start of the experiment, so time equals 0. So I don't want to keep writing the concentration, so I'm going to divide out the units, and we're going to originally start with, say, 0.1 moles per liter, and the original concentration of carbon monoxide, so I can go ahead and make that, say, also 0.1 moles per liter. And then I can measure the initial rate, so I can mix these things together, I can get the reaction going, and right in the first few seconds or so, I can measure the rate. The rate of the reaction will be in terms of a change in concentration with time, and I don't want to keep writing those units out, so I'll just divide them out to give me a number, and maybe the first run, it's 0.0021 molarity per second. So that is my very first data. And because I'm only measuring one thing, I really can't solve for 3 other things. So I do another experiment, and maybe I'll write this one in blue. And experiment 2, we double the concentration of NO2, and we leave the concentration of carbon monoxide exactly the same. And what we find is that the rate now is a lot faster, 0.0082. So we can actually look at this and we can actually see what's going on here. So going from experiment 1 to 2, we're really only changing one thing. We're doubling the concentration of NO2, and notice the concentration of CO is exactly the same. So the rule of 1 is often used here, so we just change one thing at a time, and we can see that the rate itself is essentially going up by a factor of 4. So sometimes we have to round a little bit, right? So 4 times 0.0021, I think, is 0.0084. But we can see it's pretty darn close to that. So that allows us to say one thing here, right? So I'm going to write this at the bottom. We can say that the rate is proportional to the concentration of NO2. And, well, if it's directly proportional, then if we doubled this, we would double the rate. But because it doubles here and goes up by a factor of 4, that power must be 2, because 2 squared is 4. So that gives us one bit of information here, right? So we've got the order with respect to NO2 must be 2. So now we do another experiment, and maybe I'm going to write that in yellow. And so we'll go ahead and we'll leave the concentration of NO2 exactly the same from trial 2, so there's no change there. And maybe we'll double the concentration of carbon monoxide. And so the rule of 1 applies here, so we're just doing one thing. And then we notice that the initial rate is 0.0083. And we look at that and we say, well, it's a little bit faster, but we're going to go ahead and say that it really isn't changing by much at all. It's changing by, a percent or so. So we're going to essentially assume that that is no change whatsoever. So what does that allow us to say? Well, if the rate is not dependent upon the concentration of carbon monoxide, right? We doubled it and it had essentially no effect whatsoever, then, well, you might say, well, can't we just ignore it? And yes, we can ignore it. And one way to ignore it is to take the power or the order to be 0, because if you raise anything to the 0 power, it just equals the number 1. So whatever this value is, if you raise it to the 0, it just becomes the number 1. And so then the rate there is not changing at all. So we've got our 2 bits of information here. And at the end of the day, right, we need one more thing here to solve for. So we have solved for x. And we have solved for y, so x, right, was the order with respect to NO2, and y was the order with respect to carbon monoxide, and the last thing we need is the rate constant itself. And so at this point here, we can rearrange the expression, and we can say that the rate constant K is equal to the rate over the concentration of NO2 to the x times by the concentration of CO to the y. And that's what we started with, but of course we've now determined the value of x and the value of y. So let me go ahead and delete those and replace them. So we know that x is 2 and y is 0. And of course something to the 0 power is just 1. So I'm going to go ahead and I'm going to erase this whole thing here, because in essence, right, if I divide by 1, I haven't changed it at all. And now I can plug in any one of the 3 trials above in order to calculate my rate constant. So I'll pick trial, what do you want to do? Trial 1, and I get the rate is 0.0021. I need to put the units back in, so molarity per second. And the concentration of NO2 was 0.1 molar. And I'm squaring it, so I got to be a little bit careful here, because I don't just square the number, I square the unit as well. And if I go ahead and plug that in on my calculator, we get 0.21. I'm going to squeeze it down below. And what are the units? So I've got molarity on the top, I got molarity squared on the bottom, so I'm going to have, if you like, 1 over molarity, and there's also a 1 over second. So I got molarity to the -1. Right, there's another way to write 1 over molarity seconds to the -1. So we're done.